Look at this buildup. If you've ever scrubbed at a cloudy ring around your bathtub drain or pulled spotty dishes from the dishwasher, you know how stubborn this residue can be. This residue marks a chemical clash between your tap water and traditional soap. Hard water is a common plumbing reality, which means millions of people fight this unseen chemical battle every day. Over the next 5 minutes, we're going to conduct a side-by-side experiment so you can see exactly why this buildup happens and how modern chemistry solves it. To follow along, you'll need the items shown here: 2 clear test tubes, tap water, liquid soap, liquid detergent, 2 clean droppers, and a marker. Understanding the baseline ingredients of your household cleaners is the first step to mastering your environment. Step 1 is setting up our lab environment. Take a marker and clearly label your first test tube, soap, and the second tube, detergent. Pour exactly 10 milliliters of tap water into both test tubes to establish an identical baseline. If your home has a water softener or naturally soft tap water, dissolve a small pinch of Epsom salt into the tubes now to artificially harden the water. Now for our first variable. Take your dropper and add exactly 5 drops of true liquid soap directly into the tube labeled soap. Before we proceed, put that dropper away. You must use a brand new, uncontaminated dropper for the next step. Take a fresh dropper and add 5 drops of liquid detergent into the tube labeled detergent. Isolating these variables ensures that any difference we see later is caused by the cleaners themselves, rather than a contaminated dropper. Cap both test tubes tightly to prepare them for the physical stress test. We need to simulate the friction of a washing machine or your hands scrubbing together at the sink. Hold 1 tube in each hand and agitate them vigorously for exactly 15 seconds to ensure they receive equal treatment. Stop shaking and place both tubes in a rack for immediate visual inspection. Look closely at the soap tube first. You'll notice clear markers of failure. There is barely any foam, the water is cloudy, and a white, curdy solid is floating in the liquid. The detergent tube shows a different result. The water underneath remains clear, and it's topped with a thick, abundant layer of foam. That white solid in the soap tube is what we call scum. Seeing these two liquids behave so differently under the same conditions confirms they are built using very different chemical blueprints. To understand what has happened, we have to look at water at the microscopic level. Those floating particles labeled calcium and magnesium are the hidden culprits that make water hard. Traditional soap is made of the sodium salt of a fatty acid. When that molecule enters hard water, its chemical end acts like a magnet, pulling those calcium and magnesium ions directly onto itself. This binding process creates an entirely new substance, an insoluble salt. This heavy, rigid structure is the scum you saw in the first test tube. Because the soap molecules are consumed while creating scum, there are none left over to generate lather or clean your surfaces. Detergent is a sodium salt of sulfonic acid. Its charged sulfonate end has a different reaction. The calcium and magnesium particles bounce off it harmlessly. Since the detergent molecule ignores the hard water ions, it remains free to build foam and lift away dirt. Molecular structure dictates cleaning power in hard water, regardless of how much you scrub or how much product you pour in. Looking back at our 2 test tubes, you have now visualized a chemical reality that remains hidden to most people. This non-reactive property is why commercial washing powders, modern shampoos, and liquid dish soaps are formulated with detergents instead of traditional soaps. If you live in an area with hard water, audit your household cleaners and consider swapping fatty acid soaps for sulfonate detergents. Making informed, chemically backed choices is the only permanent way to eliminate household struggles like soap scum.